On July 6, 1962, the Nevada desert seemed to turn liquid. A 104-kiloton nuclear device, buried 635 feet underground, lifted roughly 12 million tons of earth and left a crater 1,280 feet wide and 320 feet deep. The blast did exactly what its designers wanted. It excavated a gigantic hole in seconds, and for a moment, that crater looked like the future of construction. American planners imagined nuclear harbors, highway cuts, a new canal between the oceans, and gas wells fractured by atomic force. The physics worked, yet within little more than a decade, the entire idea was collapsing. The reason was not that the bomb failed to move rock, it was that moving rock was the easiest part. The program was called Plowshare, after the biblical promise to turn swords into plowshares. The Atomic Energy Commission created it in 1957, during the optimistic age of atoms for peace. Nuclear energy was being presented not only as a weapon or a source of electricity, but as a general-purpose industrial force. Edward Teller and researchers at Lawrence Livermore argued that controlled underground explosions might perform work too large or too expensive for conventional machines. The attraction was simple. A nuclear device could be lowered through a narrow shaft, yet release the energy of an enormous excavation fleet. If engineers learned to shape that energy, one detonation might replace years of drilling, blasting, loading, and hauling. Plowshare was not conceived as a single megaproject. It was meant to become an entire construction technology. Its ideas fell into two broad groups. The first was nuclear excavation. Bury a device close enough to the surface, and the expanding cavity would throw broken rock upward, leaving a crater. Arrange several devices in a line, and their craters might join into a canal, a harbor, a reservoir, or a transportation cut through a mountain. The second group was underground engineering. Place the device much deeper and the surface might remain intact. Rock nearest the explosion would vaporize and melt. As pressure fell, the cavity roof would collapse into rubble, forming a vertical chimney. Farther out, the shock wave would fracture the surrounding formation. Those new cracks might release natural gas, expose ore, or create underground storage. On paper, this looked controllable. In reality, a nuclear explosion was a one-shot machine working inside geology that could not be seen. Engineers could select the depth and explosive yield, but they could not steer every fracture, inspect the rock during the blast, or retrieve radioactive material fused into the cavity afterward. Plowshare would spend years discovering the difference between releasing energy and controlling a project. The warning appeared during the program's first official nuclear experiment. Project Gnome was detonated in December 1961, 1,184 feet beneath a salt formation near Carlsbad, New Mexico. The blast created the underground cavity researchers expected, but the material sealing the tunnel failed immediately, allowing gases from the detonation cavity to vent through the shaft and into the atmosphere. Gnome proved that the underground space could be created. It also showed how one failed barrier could turn a contained experiment into a release path. 7 months later came Sedan, the most convincing demonstration of nuclear earth-moving. The desert rose, folded, and collapsed into a crater large enough to remain visible from the air more than 6 decades later. The force registered seismic energy equivalent to an earthquake of roughly magnitude 4.75. For anyone trying to sell the technology, the images were extraordinary. But Sedan also revealed the business problem hidden inside the spectacle. The explosion did not produce a clean excavation with reusable spoil waiting beside it. Radioactive material became mixed with the soil ejected from the crater and deposited around the test area. The same physical process that removed millions of tons also created the contamination problem. There was no separate bucket that could dig without irradiating, no filter that could be added later, and no second attempt if the fallout pattern was unacceptable. That flaw became much harder to ignore when Plowshare moved beyond a closed test range. Project Chariot proposed excavating an experimental harbor at Cape Thompson on Alaska's northwest coast. One design called for 5 nuclear devices with a combined explosive energy of about 460 kilotons. The harbor was supposed to demonstrate that nuclear excavation could create useful infrastructure at a scale conventional blasting could not match. But Cape Thompson was not empty. The site was near Point Hope, an Inupiat community whose food, travel, and culture depended on the surrounding land and sea. Federal agencies conducted more than 40 bioenvironmental studies between 1959 and 1962. Residents and scientists questioned why a harbor was worth the ecological risk, especially when there was no clear commercial demand for it. Strong public opposition stopped the project. No nuclear device was brought to Chariot, and the harbor was never built. Chariot exposed a deeper weakness in the Plowshare sales pitch. The program often searched for a useful project that could justify the technology, rather than beginning with infrastructure that customers urgently needed. A spectacular harbor was not valuable merely because it could be blasted into the coast. It also needed ships, trade, local consent, and an economic purpose strong enough to carry every environmental and political cost. The same problem followed the dream of a new sea-level canal across Central America. Nuclear excavation promised to remove astonishing volumes of material quickly. But any route would also have to manage fallout, seismic effects, international borders, communities, and waterways. A major study ordered in 1964 eventually concluded that the existing Panama Canal was not expected to exceed its capacity until 1995. The most dramatic potential customer for nuclear excavation did not need the product urgently enough to accept its risks. By the middle of the 1960s, Plowshare began shifting away from open craters and toward a use that seemed easier to contain: natural gas. Tight sandstone held large volumes of gas, but the rock did not allow it to flow efficiently into ordinary wells. A deeply buried nuclear explosion might create an enormous fractured zone while leaving most radioactive material sealed underground. Project Gasbuggy tested the idea in New Mexico in December 1967. A 29-kiloton device was detonated 4,227 feet below the surface. The rock collapsed into a rubble-filled chimney, and a re-entry well was drilled into it. Across 5 production tests, the well produced 213 million cubic feet of natural gas, more than nearby conventional wells. For the first time, Plowshare appeared to have created something an energy company could measure and sell. Then the laboratory results arrived. The gas contained measurable radioactivity. It also had a significantly lower heating value than expected, and the explosion had created fewer useful fractures than planners predicted. Gasbuggy had increased production, but it had not produced an ordinary commercial fuel. The project succeeded as a physical experiment and failed as a product. That distinction mattered. Contamination did not need to escape into a town for the investment to collapse. If radioactive material remained in the cavity, the government inherited a controlled subsurface site. If radionuclides came up with the gas, the company inherited fuel requiring special measurement, handling, and approval. Containment could protect the public while still destroying the business model. Project Rulison repeated the experiment in Colorado in 1969 with a 40-kiloton device buried about 8,425 feet underground. The re-entry well later produced 455 million cubic feet of gas during 107 days of testing. Radioactivity in the produced gas declined as testing continued, but it did not disappear. The Department of Energy's current history states the result plainly: the gas remained unmarketable. The final attempt, Rio Blanco, tried to solve the geology problem with 3 devices detonated almost simultaneously at different depths in one Colorado well. Planners expected the 3 collapsed chimneys and fracture zones to connect, forming a tall underground production system. Testing showed that they did not connect, and the fractures extended less far than predicted. The blast energy was immense, but the rock still decided where the cracks went. By this point, the failure was no longer theoretical. Nuclear stimulation required specialized devices, security, drilling, radiological monitoring, cleanup, and permanent controls. By 1974, about $82 million had been invested in the gas stimulation program. An official history estimated that even after 25 years of producing all the gas considered recoverable, only 15 to 40% of that investment would be returned. Meanwhile, conventional hydraulic fracturing was improving. It could be adjusted, repeated, and deployed without leaving a nuclear cavity beneath a commercial field. Plowshare's supposed advantage had been scale, but scale became a liability when the geology behaved differently than predicted. A conventional treatment could underperform and be redesigned. A nuclear treatment could underperform once and create a site that still required government responsibility decades later. The official record counts 27 Plowshare nuclear tests containing 35 individual detonations between December 1961 and May 1973. The tests generated useful scientific data about underground explosions, geology, radiation monitoring, and emergency response. But no commercial nuclear excavation or gas stimulation industry followed. Economic pressure, environmental concern, public opposition, and better non-nuclear alternatives ended the program in the mid-1970s. Its physical legacy is more complicated than a simple disaster story. Surface cleanup was completed at Gasbuggy, and the land returned to recreation and grazing. Monitoring has not found Gasbuggy-related contaminants in sampled nearby gas wells. At Rulison and Rio Blanco, monitoring has likewise found no evidence that test-related radionuclides have migrated into the sampled surrounding water or gas systems. But absence of detected migration is not the same as absence of responsibility. Subsurface contamination remains in the nuclear cavities. Drilling restrictions and institutional controls protect those zones, while the Department of Energy continues inspections, sampling, modeling, and record-keeping. Gnome, Gasbuggy, Rulison, and Rio Blanco are no longer active experiments, yet they are still managed sites. That is the real lesson of Project Plowshare. Its engineers treated the explosion as a moment in a construction schedule. The legacy turned that moment into a permanent relationship between the government, the land, regulators, nearby communities, and every future company that might want to drill there. Plowshare did not fail because nuclear devices were too weak to transform the landscape. Sedan proved they were powerful enough. It failed because infrastructure is not measured by the size of the hole or the first burst of gas. It must remain useful, financeable, acceptable, and manageable after the construction crews leave. The Sedan crater still exists in the Nevada desert, enormous and technically impressive. It is the clearest monument to the program's mistake. Plowshare tried to turn the most destructive machine ever built into the ultimate construction tool. Instead, it demonstrated that the hardest part of a megaproject is not forcing the world to change. It is controlling what happens next.